So shall we be exactly? I like your notes. Okay, thank you very much all for coming on Friday afternoon. And thank you for the Physics and Engineering Students Club for arranging this talk, as well as all the nice goodies that we have here. It's always fun. So the title of this presentation is What is Superstring Theory and What Can You Do About it? In a sense, I'm going to go over the theory itself, and please feel free to ask questions at any time. And the part about what you can do about it is towards the end, where I explain my own research program for undergraduate students particularly. So it is broken down to the following topic. String theory came as a solution to a number of problems, a number of open questions. And to understand why it's important, you have to understand first what are the problems. So I'll give you a little bit of background on the two versions of the two models of nature that we usually look at, the classical and the quantum. And the standard model is the quantum version of fundamental physics, as we'll see. We'll talk a little bit about classical gravity, Einstein's theory, and then the problems that arise from all of this, and string theory as a solution. Then there is a version of superstring theory called supergravity theory, sort of the classical version of it. And I think I'd like to describe this because that's, hey, come on. No, you just started. So supergravity is important to describe because it is what I do mostly, more than the quantum version of it. So classical physics, that is the version of physics that we're all familiar with, and every undergraduate student is familiar with. It is the version where there's essentially no quantum mechanics. If you want to explain the forces of nature, you explain them via something known as vector fields, which is due to Michael Faraday. It's important to note and to remember, and there goes and it's important to note and to remember that the classical fields live and propagate in space-time, space and time, in being the key word here, and that will come back later to haunt us. One thing I want you to keep in mind is the classic problem of two moving charged particles, two electrons approaching each other, one electron going this way in a straight line and one electron moving that way. We observe in the lab that they don't collide. They're repelled, and one goes this way and one goes that way. And the classical version says this happens because there is this infinite and invisible field that fills up all space, and that field pushes the other field, and they just slide off each other. This is the classical version of things. The quantum version of things on the picture is a little off for some reason. Give me 1 second here. Give you the original. PowerPoint would be better. Okay. All right. Skip. Yes. Well, still. That's weird. What is it?
You're going to enable editing first at the top.
Thank you. Move it off, maybe it's the
Not that I've
colors.
made that mistake myself a billion times.
Thank you so much. Yeah. So back to it again. I think if I move it up, it's important to see this kind of slide. Yes, definitely much better.
Bring it
Well,
to the front. Right,
Thank you. I am glad to have an expert in PowerPoint documents. Yeah, that should.
Yeah, you brought it in before, not on the Xboxes.
Anyways, here's the picture in the original version. Unfortunately, I can't show you the animated version because of this glitch. I don't know what it is. So you remember the two electrons approaching each other, and because of the classical fields, they kind of move away from each other because of an invisible force. This is the classical version of things. The quantum version of things is a lot weirder. The quantum version of things says, if I have two electrons approaching each other, at some point, one electron, random, of course, it's quantum, emits a particle. And that particle travels a certain distance, collides with the other electron, and because of conservation of momentum, one has to go this way and one has to go that way. Now, you might think this is a very weird explanation of why electrons divert each other away, but if this happens in consistent and an infinite number of times in a very short period of time gives sort of the illusion of the classical smoothness that happens. Again, as usual, this is quantum mechanics. So when you think it's weird, well, it's quantum mechanics. So one way to visualize this, because of momentum conservation, is the picture of two people standing on skates on ice. And they start exchanging oil. Because of momentum conservation, one of them has to go this way, and one of them has to go this way. And this happens a very large number of times, and you get smooth transition. They can, of course, attract each other by throwing a boomerang, basically, that goes around, and conservation momentum makes them attract each other. So momentum conservation can happen either way. It's either repulsion or attraction. That would be the quantum version of the classical fields. Well, based on all of this, we come to what is known as the Standard Model. And the Standard Model is a collection of theories that are all based on this idea of particle exchange. Foremost among them is the one that you and I are most familiar with, the theory of electromagnetic field. The electromagnetic field classically is described by the Maxwell equations. And that version of the Maxwell equations is kind of a compact version. You may have seen it at 415 as 4 equations. There's a way to write it as 2. And that would be the classical version. But it is a particle exchange theory. So instead of the classical field, you get those exchange particles. A second force that is studied under this Standard Model is the so-called strong nuclear force, which is essentially the force that keeps the nucleus together. I mean, I don't know if you've ever thought about it, but a nucleus is made up of a bunch of protons and a bunch of neutrons. All the protons are positively charged, so according to electromagnetism, they should repel each other, but something is holding them. What is holding them is this so-called strong nuclear force. The third force of nature is also something that happens inside the nucleus. It's called the weak nuclear force. I mean, I don't know who came up with these names, but it's not very imaginative. They just describe the strength of the force, but they don't have a fancy name. Just the weak force and the strong force. The weak nuclear force, as far as we can tell, is responsible only for radioactivity. So every once in a while, an unstable nucleus, as we all know, emits a particle, like an alpha particle, a beta particle. This comes from weak nuclear interactions. Those three forces are what constitutes the Standard Model. And they're made up of particles and exchange particles. I'm not saying fields anymore. You've got particles, like the electron. You've got particles, like the quarks, up, down, 6 types of quarks. You've got particles like the muon. But then you also have exchange particles. The photon is the exchange particle, remember the conservation of momentum, between electrons. The gluon is the exchange particle between quarks and explains the strong nuclear force. The so-called W and Z bosons are exchange particles for the weak nuclear force. Altogether, those three forces, or all the set of particles, however you want to look at them, constitute the Standard Model. All the forces of nature explained in one model except one. There is only one force of nature that is missing from this picture. And that would, of course, be gravity. To this day, we don't have a quantum version of gravity. That's one of the main problems that we have. String theory is an attempt. I mean, it's one of the attempts to make gravity into a quantum field theory, just like the other three forces. But it's not definite, because we don't have experimental verification. It's lacking. There's no experiment to explore the quantum nature of gravity. That is in part due to the fact that gravity is a very weak force, and in order to study it, you must have extremely sensitive equipment, which we don't have. It requires technology that is not available. So the only way we can do it is to explore it classically, to look at gravity and say, what is the classical field, not the quantum field, that describes gravity? Well, it turns out that the classical field that describes gravity is space and time itself. I'm sure everybody knows, even if you haven't studied in detail, that the general theory of relativity describes the curvature, if you will, of space and time. Put together, we call them space-time. What happens, or what we think happens, is that the presence of energy and mass tells space and time how to behave. And at the same time, space and time can also tell mass and energy how to propagate. So it's a sort of two-way street when it happens to Einstein's theory of general relativity. It's usually depicted by a picture such as this. I mean, it's a nice model to think of a trampoline surface with everything is nice and elastic. You put a mass in the middle, it bends space and time around it. Or if you wish, 3D like that, where each one of those lines represents what would otherwise be a flat, essentially. It's just like a flat meter sticks, if you will. So just as the presence of mass and energy tells space and time how to behave, the opposite is also true. Now I can, space and time, when it's bent and something moves into it, it simply follows curves of minimal length into this space and time. Just like when you drop a bar of soap into a sink, it doesn't go in a straight line, it goes into complicated curves. It's following the curvature of space and time. On a side note, the problem of a slippery piece of soap in a sink is studied in classical mechanics in 420. And I've always noticed that the mathematics that you use to describe this is almost identical to the mathematics that you use to describe this. At least you end up with the same weird, complicated differential equations that need a computer to solve. I've had, in fact, one of my former research students model a general relativity problem on a problem that we had in classical in physics 420 earlier. So this is the classical version of gravity, but what's the quantum version of gravity? People tried. They have spent, I don't know, at least since 1915, when general relativity came out, until the early 70s, just trying to quantize it in one way or another. But remember, the quantum fields of the classical standard model are particles and fields that propagate in space-time. So when you quantize it, this is one story, but how do you quantize space-time itself? This is what general relativity is. It is space-time itself. How do you quantize it? That's a problem. In addition to string theory, there are other models attempting to quantize gravity, but I'm not going to mention those today. The competing models, if you will. So, is this the only problem with our current understanding of fundamental physics? Well, yeah, quantizing gravity is not the only problem. Other problems with the standard model is that we don't know why the particles have the masses they do. If I go back to the previous slide, this one, here are the masses of the particles, given in units of GeV, giga electron volt per c squared. And no idea where these numbers come from. Nobody knows. We just measure them experimentally. But there's always the nagging feeling that those masses must have a reason. I mean, we want to find what are the basic principles of the universe, and the basic principle of the universe should be able to tell us, well, the particles have this kind of mass or this type of mass. So that's a big problem as far as fundamental physics is concerned. Also, why is it that certain forces are not just stronger, they are much stronger than others? Look at this nice curve here. The vertical axis is the strength of the force, any force of nature, and the horizontal axis is the scale size, or energy. Scale size in the sense of what? Since the smaller you look, the higher energy you're going to have. We are here, somewhere. This is our scale. This is human scale. We see the strong nuclear force is the strongest force that we can detect in nature, followed closely by electromagnetism, and then followed closely by the weak nuclear force. But then way down there is gravity. Gravity is so much weaker than all of them together. It is assumed that as you look deeper and deeper into scale, all of these forces kind of come into one, and their strength become the same. We've already verified the first point. Electricity and magnetism can become the same thing as electroweak, and we have experiments all the way down to here. But we don't know what happens in here, where it's expected that electricity and magnetism, weak and strong, would become the same, and we have no idea what happens here. In cosmological terms, you can think of this graph as history of the universe, where the Big Bang is to the right. And as the universe expanded, its energy density became less and less, and the forces started to break up. They started all as one force, some scale, very small area, very small volume, and then the universe is expanding and we're losing, essentially. The forces are breaking up, in a sense. We don't know why. We'd like to know why. There are also mathematical problems. There are infinities that appear in the standard model that are a little weird, and they have always been thought of as sign of an internal structure that we're not seeing. In other words, we're assuming the particles to be made of points with zero size, but that is not working very well. So one solution, I mean, this slide is claiming that it is the solution, but one possible solution to all of these problems is string theory, or superstring theory. I don't know if anybody remembers this music. Okay, that's enough. Presumably, it's a model that unifies all forces of nature. Presumably, all forces of nature come out of it automatically. You don't have to make any assumptions. Theorists love this. They love starting from a fundamental set of axioms, and everything just comes out beautifully. You don't have to say, oh, let me put in gravity and see how it works. No, they want to see gravity coming out of the model, and that's what happens here. It explains a lot of the problems in the old quantum model. For example, predicts to some degree the masses of the particles. Predicts the hierarchy problem, which is the difference in energies, the difference in strength of the forces, and so on. They're all just one entity. They're all made up of the so-called superstring. So it is a matter of scale, like I pointed out. I mean, up to, at least experimentally, up to today, we are at this level. We are seeing the subatomic particles as just points and dots. It is assumed that if you look closely enough, each one of those points is made up of a fundamental string that is vibrating. They're all the same. I'm not saying they're different strings. That's the beauty of it. There's only one superstring. It vibrates just like a string from a violin. Vibrates in a certain way, you see electron. Vibrates in another way, you see a quark. Vibrates in a third way, you see a photon, and so on. So the whole universe is made up of one, well, not one, but the same type of superstring. Where does this number come from? Good. All right. Remember this version of things. I told you that in the standard model version, here is the scrambled up picture. Electrons travel, and then something gets emitted, and then one electron goes in one direction, another electron goes in another direction. In the string model, it's not quite what happens. There's no electron or photon. It's just one string. Approaches, combines, and then leaves. Same string, and changes the vibration in the middle. That's fine, because when you're looking at it from here, you're detecting an electron. You're looking at it from here, you're detecting a photon, and so on. It's very smooth and very elegant. The super part, I mean, that's the string part. The super part comes from something called supersymmetry, which is a long story, but it's also a byproduct of the string theory, meaning it comes out of it naturally. Supersymmetry is a symmetry of nature that predicts that matter particles and force particles have siblings, essentially. Remember, electrons and quarks are matter particles. Matter is made of them, right? They're fermions. Exchange particles, like photons, like gluons, like the W and Z particles I pointed at earlier, are bosons, and they are force particles. They're exchange particles. What supersymmetry presumes or predicts is that for every boson, there exists a fermion. Siblings, they have very similar properties, and one can exchange into another. Look at it. We see photons in nature, we see gluons, we see Ws, we see Zs. So these are observed. We see electrons, of course. We see quarks. We don't see the gravitino yet, but these are matter particles. Over here are the presumed supersymmetric particles. So an electron string would have a super electron string, pronounced selectron, and its quark, and so on. While the photon would have a photino, again, unobserved, but presumed. gluon, gluino. The W, the wino. And Z, zeno. Now that's creative. That's better than strong nuclear forces, weak nuclear forces. Okay, nice! We have a theory that is the foundation of everything in nature. Please don't be mad at me when I say that physics is a foundation of chemistry, right? Now, and chemistry is a foundation of biology, in a sense, in a fundamental sense, and so on. What we're looking at is something that is the foundation of all theories.
You've got the base of that wrong, right?
Right, but I'm talking about the science, the material sciences. But you're right, of course, math would be the foundation that's below even all of these. But in the sense of a science that I can experiment with in the lab, this is what string theory is supposed to be. It is a toe, a theory of everything. A dream throughout the ages. All nice and fine. Everything has been unified. All the fields in there. Gravity is included. The infinities we observed in the calculation before are gone. Complete unification. Are there any problems? Yes, of course. Natural question. If electrons and quarks and particles and photons and photons and winos and xenos and all of that stuff is made up of a string, a certain fundamental string. What's the string made of? We don't ask that question. Shh. We pretend the question doesn't exist. When somebody corners a superstring theorist in the corner and says, "What's a string made of?" They say, "It's a fundamental string." Moving on. It's fundamental. It's not made up of anything. It is the base foundation. You can't say it's made up of anything. Like a prime number. Foundation of mathematics. And that's it. Moving on. Don't ask me that question. It's blasphemous. String theory also predicts unobserved particles. And a lot more than the ones that we're hoping to find. The supersymmetric ones. In fact, an infinite tower of them. String theory has not been observed in the lab. And that is one of its biggest problems. It does not, so far, present any experimental verification. And it gets worse. String theory requires, it's not a side effect, it's a requirement. Without it, you have to scrap the theory and throw it in the trash. It requires the presence of higher dimensions, all the way up to 11 space-time, which means 10 spatial dimensions. We live in 3. Time is the 4th. String theory requires 10 plus time. It's a total of 11. Oh my God. What are you supposed to do with that? It was a problem. But string theorists are a very resourceful bunch. They always come up with solutions. They said, look, if string theory needs it, it must exist. We take it on faith. It's an article of faith. We will just assume that the extra spatial dimensions that we don't seem to observe are either A, very small. They are curled up into very small curves. An example of this, a straight line that you see from far away, garden hose. You think one dimension. When you get close to it, you find that there is a circle, there is an extra dimension. There is another way to go around it. It's very small dimension. So we assume that every point in space and time that exists an extra, well, shall we say, curve or surface that is made up of the 6 extra dimensions that is all bundled up in a very small scale. This is called the compactification solution. One way to solve the problem. Another way to solve the problem, and today we think it's a combination of both, is that for some reason, our strings are constrained to live only in 3 dimensions, and the rest of the extra dimensions are just out there. We cannot reach into them because we are made of strings, and strings cannot leave this universe, if you will. So this is called the bulk theory, or the parallel universes theory, that says there is extra dimensions, but we can't reach into them. We're constrained from moving into the extra dimensions. The way to explore all of this is to just sit down and do the math. I mean, we have really no way of exploring any of that experimentally, although in recent years there have been some speculation. Next version of string theory that I would like to look at is so-called supergravity theory, which is essentially string theory in a classical form. So instead of looking at the strings as individual strings with quantum particles with quantum properties, we simply look at them as fields, and stringy fields, if you will. They have strange properties, but this is a very classical way of doing things. It's got supersymmetry, it's got gravity, it's got all the rest of the strings. It is sort of a toned-down version of string theory. And it's useful for many reasons, because string theory is the full quantum mechanical string theory is sort of, well, non-perturbative. I mean, it's made up of infinite series and stuff, while supergravity is non-perturbative. So you can study effects that don't show in string theory. That's, the properties of supergravity or supra. It's got supersymmetry, it's got classical fields, the stringy fields appear to propagate in curved spacetime, and so on. So this is a kind of toned version. It is also the version where something very strange pops up. A string is a one-dimensional object, it's a filament. It turns out that there are other solutions of the theory called the branes, higher dimensional versions of string. A one brane would just be a one-dimensional filament strings. 0 brane, that would just be a point. 2 brane would be a membrane. And then we've got 3 branes and 4 branes all the way. I think I've seen up to 7 branes. These are byproducts of the theory, and at first theorists felt that they don't have a reason to exist except that they are mathematical entities that show up in the math. But in the 1980s, somebody discovered that they are dynamic, meaning that they can propagate and interact with each other, which makes them physical. And now the question becomes, okay, we are in even further trouble. If you're going to talk about strings, now you're going to talk about branes. What are the branes made of, and where are they, and where do they come from, and what exactly kind of application are we talking about here? Yeah, we like branes, that's definitely true. They are considered elementary. I mean, just like strings. And today when you say superstring theory, you don't really just mean strings anymore. You mean everything that goes into it. One possible application that people seem to like very much is that maybe branes are things that are too big for us to observe rather than too small. Strings are too small for us to observe, but branes are too big for us to observe. Consider the possibility that our own universe is, in fact, a 3-brane. And that higher dimensional branes can exist outside of that, outside of the bulk. This is one application that people have been considering for a while, especially since it solves the extra dimensional problem. It means that we've got one universe, 3 branes, another universe, 4 branes, another, and so on, which you can go as much as you want. This is the picture that I was talking about earlier, the brane world scenario. Our universe is just one of those branes, and then there are higher dimensions that we call the bulk. And then there's another universe somewhere, and maybe they can interact. There was an interesting paper that I was asked to review for Scientific American a while back that seems to indicate that some astronomical anomalies far into the deep Hubble field, like really deep space, may have the interpretation, some anomalies in the cosmic microwave background, may have the interpretation of 2 universes touching each other. So we may be able to observe the existence of a parallel universe or a parallel brane if they touch, and there's no reason for them not to. They can touch, they can collide, they can cross over. They're just floating around randomly in this higher 11-dimensional space. The universe is much bigger than one thought thinks, if this is correct. It's a big if. So that would be nice. This brane world model would really be interesting if it were true, and people got very excited about it because it just explains a lot. Branes in supergravity can be studied mathematically just as you would study charged particles with fields. You consider, instead of point particles with fields, you look at charged branes with strings, essentially. And one string can start with one end and the other, or can propagate from one and attach itself to the other, and all of these things. There are analogous situations to everything you find in ordinary vector field theory that you can find in superstrings or in supergravity or any of those versions of things. So we come to the part where I tell you a little bit about what I'm doing. I look nice in this photo, right? Funny thing is, that I spotted an actual number here. It's 137 is called the fine structure constant. It's of the electron. So I don't know if that was intentional or anyways. So
Why not? They've got pi, HC, and G, they're all real.
yes, but the units are off. I mean, if he means that this, well, no, not really. If this is a mass, then that might be right.
And I know the writers of The Simpsons got PhDs from Harvard in mathematics.
Really? Well, okay, that explains it. And the presence of donuts is not surprising, by the way, because
Maybe not Harvard.
those microscopic surfaces I'm telling you about that exist at every point in space, they have topologies that can be explained by things like donuts. I don't want to go off. But anyways, Homer Simpson. So I work in supergravity most of the time, and I'm most interested in how brains interact, and I'm trying to find applications for them that we can find in the real world. I've worked in 11 dimensions, 5 and 4. I will give you examples in a bit of what I work in. This is just a little idea of how does one become a string theorist. And it's just, the field has expanded so much that I'm not aware of any one person who knows all of string theory. I mean, it's really strange. This is a theory that has had no experimental verification, and yet has solved so many important questions, so many important problems, theoretically, that it has persisted, and people are still working on it, and it's expanded mathematically as far as things can go. So if you want to study string theory for a career, then it would feel like you're taking every kind of physics and math that exists. It would feel like that. And it's a lot of effort, a lot of sleepless nights. And then you still realize that you haven't even scratched the surface. But you gotta stop somewhere. So the question now becomes, is it too complicated for a student to work on it? And that student is still in their college years. I've discovered by experimenting, trial and error with students, is that it's not impossible. It's doable, and I'm working with some of them right now. Usually what I ask students to do is to study a little bit of relativity. Relativity is absolutely essential, both special and general. Then we study a little bit of classical and quantum field theory, depending on what the problem is. There's a branch of mathematics called differential geometry and topology that also may be needed, again, depending on the problem is. So usually what I ask students to study depends on the problem I'm going to assign them with. So if I know ahead of time that their problem requires a little bit more of this than it is of that, then we don't waste time with this and kind of focus on what is needed. Doesn't quite make you a string theorist, but it does give you a glimpse of the overall picture, and you do get to do a lot of work. Because the big picture is so big, and as I said, I don't really know anybody who knows all of the big picture, I require reading popular books. Like books that are written for the layperson, for books that are written for the non-expert, the non-physics major. Because they tend to give you a lot of information in a very short period of time. You don't have to study all the mathematics behind it to understand what's going on in the big picture. So that is something I require. And then we can practice, if we have time, practice with previously known results, work on your own problem. And along the way, people have found that they learn things like Mathematica, writing papers, and so on. And it all depends on how much time you have left before graduation, and it depends on how much time you're willing to give to do this. There are several possible outcomes to students doing research with string theory. Outcome number one, you get to learn something that you wouldn't have learned otherwise, and you move on. Outcome number two, you get to do research, and you get to give presentations, maybe transformations, maybe even undergraduate student conferences. There's one in Rochester every year that have had students present in before. And outcome number three is you can get to see your name on an actual published paper in a peer-reviewed journal. That has happened so far with me twice. And the third is on the way. We're working on it right now. This was my first undergraduate student who persisted and made it to the very end and managed to publish a paper. This was a paper where we were modeling our universe as a free brane embedded into the high-dimensional bulk, and using that model in a certain supergravity theory to solve the so-called cosmological point constant problem. Some of you may have heard of this before. The second student that survived with me was Jesse. Some of you may remember him. He only graduated last year. I don't know if you met him before. He studied the motion of photons around a specific type of supersymmetric solution, and that was published. Currently, I'm working with Anthony Nicolti, and he's doing some elliptic symmetry solutions in 4 dimensions, and this is one of the solutions that he found so far. Finding solutions of supersymmetry and supergravity and ordinary gravity is the easy part. Interpreting what they mean is the interesting part. That's where the fun really begins. All right, that is it. Thank you very much. So, questions?
On the one slide that showed the forces being separated. Like
Yeah.
Is it possible, like, if it were to go in the other direction and get scaled up, that there could be more forces that we don't know about?
Yeah, it is, and we don't know. The question is, no clue what happens there. But why don't we see them? I mean, theoretically, yes, it's possible.
Right.
But if you go further, that means less energy, which means this is what we live in, and we don't observe except those 4. There was some speculation at some point in time about a 5th force, which is responsible for the expansion of the universe, or could have been responsible. But then they came up with the cosmological constant and went into a different direction. But you're right, it's possible that there may be other forces that we're just not seeing for some reason, maybe I don't know, they don't apply to our life here in our very small niche in the universe.
So the thing that piqued my interest was when you were talking about the other, like, universes,
Right.
possibly touching, like, because
Yes.
it's so big, like.
And here's the fun part. Each one of those universes can have its own laws of physics. They don't have to be the same. Because there's so many different ways you can construct string theory. Other fields can come out that different from the ones that we observe. So, in fact, some people have talked about the possibility of having maybe 10 to the power of 500 possible universes. It's a very big number. And each one of them has its own laws of physics. And when they touch, crap happens, essentially. Because you've got not just 2 universes colliding. You don't have 2 forces colliding. You have 2 different sets of laws of physics colliding. We don't even know what would happen in a situation like this.
Does that have implications for what kind of evidence you would need in those cosmological experiments when you're trying to say, oh, well, that oddity could be a result of touching another brain?
Yes.
I mean, you can't predict what would be characteristic if you don't know what the laws of physics
Absolutely
would be in
right.
that brain.
Absolutely right. That's why in fact, when I review that paper that I
This
mentioned.
makes it an untestable hypothesis.
Yes, exactly. You don't really know. Yeah. Listen.
So, of course, the questions that I have are more cosmological.
Yes, please.
And so, how strongly does superstring theory depend on understanding gravity? In other words, how dependent is it on the specific general theory of relativity?
It is very dependent.
And so my question is, because I'm sure that you've heard of Milgram, and so when we're trying to explain dark energy and dark matter, and the explanation for the supposed gravitational influence of clusters of galaxies and superclusters and the accelerated expansion of the universe, there are a growing number of people who think that it is not that we need to invoke dark matter and that we need to invoke dark energy, but that we simply don't understand gravity, that possibly gravity operates differently at the large scale.
Yes.
Than it does at the
You're talking about modified theories.
Right, and so there's, Milgramian theories now.
Yes.
What are your feelings on that?
I am, okay, so there are modified theories of general relativity. So that's a very good point. Let me explain a little bit further. Do we really know? I mean, the theories, the models of general relativity that we understand are based on Einstein's field theory, which is the field equation, which is this. But there could be other terms and other details that maybe Einstein didn't predict. As far as I know, there doesn't seem to be any verification for all of these. Every local test, I mean, other than the clusters, but the large-scale universe, every local test that was ever done of generativity was confirmed by this equation and this equation alone. No need for extra terms, including the recent discovery of gravitational waves. You're correct. Yes, there are ways to modify generativity to account for the expansion of the universe. But that would also, as far as I know, and I'm not sure about that because it's probably that's more your field than mine, there are other ways to verify it cosmologically that they're not seeing.
There have been some observations that have supported Milgronian theories of gravity, and I can't give you the details because it's so far out of my
I'm not very familiar with it either.
But
if
it
there
has
are,
something to do with the dwarf galaxies. I know that. And so, when I get to this section in the astronomy class, I always, want the students to keep in mind that we aren't really certain that we understand gravity. So far, it's the best thing we have.
Yeah, it is the best thing we have.
But
And it
Newtonian
can also
gravity
be,
has already been
absolutely, it
modified.
can also be part of a bigger scale
Yeah.
theory that just like Newtonian gravity is
Exactly.
part of a bigger scale generativity.
Exactly.
But so far, the only one that we can confirm 100% is
Right,
Einstein's
absolutely.
current form. But you're absolutely right, there are ways of modifying it. The question of how all this would fit in string theory is a very interesting question.
Yeah.
I've seen a lot of papers coming out trying to fit modified theories of gravity into string theory, and they've all been touchy.
So yeah, I guess that leads me to my question.
Yeah.
If you can't experimentally detect, 90% of the mass
Right.
that our theories of gravity, general relativity tell us should exist, there's no experimental verification of that, and then there's no experimental verification of strings, then it becomes very convoluted.
It is. It is, and that's one of the main
Yeah.
criticisms of the whole model of superstring theory. People have written books saying, oh, you guys are wasting your time. If you can't experimentally verify, move on. So I wrote an article that got published in the American Journal of Physics saying, so what will I do if string theory is wrong? And I proposed an answer to them to say, okay, if it is wrong, it is too interesting and too mathematically beautiful to be thrown out entirely. It's got to become its own branch of math, maybe, where you can explore mathematical models from within string theory. As a matter of fact, string theories so far don't win Nobel Prizes. They win Fields Medals. Fields Medal is, Ed Witten is a famous string theorist. He won a Fields Medal. It's the Nobel Prize of mathematics because he managed to get out mathematical theories out of string theory itself. So if it's proven incorrect, would you throw it out the window? I don't think so. Just too interesting. It's got to have something in it. It answers so many questions. There's got to be something in it that at least has some relation to nature.
Could you maybe comment on, you mentioned the gravitational waves that were recently?
Yeah, gravitational waves are a prediction of general relativity. And they say that if space-time is this rubbery environment, then any violent event happening in it will generate waves, just like waves on the pond. But they're waves of contracting space and time. So the actual measurements in space would change as things would go. And that's why they used this interferometer, if you will, to measure the difference of the distance that light crosses in one direction as opposed to the distance that the similar beam of light crosses in another direction. And if a wave approaches, space contracts differently in this direction than it does in this direction, and you can detect that. And that's what they did. It's a major breakthrough. And the astronomical implications are going to be amazing because now you've got a new set of eyes. You can detect the universe not just by looking at its electromagnetic waves and feel like light and X-rays. Now you can look at gravity too, directly. It's going to be amazing. I'm very excited about it.
I have one more question that was
Sure.
totally unrelated, and I may be completely confused, but it seems to me like I read something not too long ago, within at least the last 6 months, that there was some type of experimental result that contradicted supersymmetry.
No, but they didn't find it yet. It didn't contradict supersymmetry.
Okay.
Not that I know of. I may have missed that.
But if it did contradict something, that would be big news. It's just that they didn't find it yet. There is a lot of predictions on the energy scale where they would find those supersymmetric photinos and MIMOs and stuff. And we're almost there in the Large Hadron Collider in Geneva, and they still don't see it. So we're kind of embarrassed a little bit right now. You know, they better find something soon. Any other questions? Thank you very much.